Welcome to this guided practice on enthalpy of phase change. First thing I want to do is take a look at this problem number 1. Describe the heating curve of methanol and label the enthalpies of phase change and their sign for delta H. And so when we look at this, we see that we're heating the substance methanol, and so the very bottom we see that it is heating the solid, and here in the middle it's heating the liquid, and of course at the top it's heating the gas. And so those are kind of the three sloped lines, and then along these other horizontal lines we see that this is where the phase change is happening. So between a solid and a liquid, if we're going from a solid to a liquid, that would be the process of melting. And so that is the heat of fusion. And the heat of fusion for us is 3.22 kilojoules per mole for methanol. Now, if I were to go in the opposite direction, and this would be freezing, then that means that my delta H for freezing would be a negative 3.22. So same magnitude, opposite direction. Same thing happens when we take a look at the heat of vaporization. So we are evaporating or vaporizing as we move from left to right, from the liquid to the gas. And so this would be vaporize or evaporate. And so the delta H of vaporization is going to be 35.2 kilojoules per mole. And then in the opposite direction, that is going to be for condensation. And that value is going to be negative 35.2 for the delta H. So same magnitude, opposite directions. And just keep that in mind. Sometimes you'll have to use that negative value instead of the positive one, depending upon the direction. So in our second question, we're asked how much heat is required to vaporize. Okay, so we are looking at vaporizing, and we already said that was the heat of vaporization, 40 grams of liquid methanol. So the first thing that we need to know is we need to know the molar mass of methanol before we go anywhere else. So molar mass for CH3OH, and so that's going to be 12 grams for the carbon plus 3 times, actually 4, there's a fourth hydrogen here. So let's get 4 hydrogens, so 3 plus another 1. So 4 times 1 gram for hydrogen plus oxygen is 16 grams per mole. And so when we total all of that up, we should get 32 grams per mole. Double check that in your calculator. And at any point along here, pause, try to work a problem, unpause, watch how it's done. All right, so we're going to take that 40 grams that we're given. So we're going to start off with the 40 grams of methanol. We're only working with methanol, so we can just do that. We're going to take our 32 grams per mole. So 32 grams is going to go on the bottom to cancel grams on the top per 1 mole. And then finally, we're going to use that heat of vaporization. And so for every 1 mole of methanol, it is 35.2 kilojoules of energy to vaporize. And so when we do our math, we can cancel our units here. So grams cancel, moles cancel, we're left with kilojoules, which is what we want. And so we go ahead and multiply across the top, so 40 times 35.2, and then we divide by 32 on the bottom. And we should get 44, it looks like we should have 3 sig figs, so 44.0 kilojoules should be our answer. In question number 3, we're asked to do this only now. It's when something freezes. Okay, so we have to remember that freezing is in the opposite direction, and so this is where we're going to see our negative 3.22. All right, let's go ahead and set this up. So we're going to have, again, still 40 grams. The molar mass hasn't changed. It's going to be a constant, so 32 grams per 1 mole. But now we need to use this other value. And so since it is freezing, we have to have a negative 3.22 kilojoules per mole. Okay. So let's go ahead and put that in. So for every 1 mole on the bottom, we have negative 3.22 kilojoules. All right, multiply across the top, multiply across the bottom, and we should get a value of negative 4.03, 3 significant digits again, kilojoules. Okay, let's keep going and work some other problems here in just a moment. But one thing I want to point out is the amount of energy that it takes to vaporize or condense is a lot greater than the amount to melt or freeze. And one of the reasons why is that in order to be able to vaporize, we have to completely break all of the intermolecular or interparticle forces on an individual molecule in order to vaporize it. And with the freezing and the melting, we are just having to either make or break just a handful of those intermolecular forces. Some of them are either going to stay intact, or we're just having to increase the number of them depending upon which way we are going. Keep that in mind. All right, I threw this heating curve down here again just to kind of keep us thinking about what's going on, and we are asked how much energy, so this is going to be total energy, is absorbed when we take 10 grams of solid methanol at negative 150 degrees Celsius and we heat it to 103.5 degrees Celsius. And we're given a specific heat as well. So we probably need to know a little bit more. When we are heating a substance, okay, so when we are heating any sort of substance, or if we are cooling the substance down, okay, it would just be opposite direction. Heating or cooling the substances, what we're going to use is Q equals Cm delta T to find out how much heat. And then, of course, when we are working this for the phase change, okay, so then for the phase change, just like up above, we are using a conversion. And so each time we are doing one of the heating, or if we were cooling this, we will be using those. And then, of course, just like we did before, we're using conversions for those phase changes. So let's go ahead and work through this problem. So the first part of it is going from negative 150 degrees Celsius to the melting point, which is negative 97.6. So that is going to be our first part. So the first part, we are going to do heat the solid. Okay. From negative 150 to this melting point, okay. Negative 97.6. Okay, so we're going to put that into our Q equals Cm delta T. So Q, which is heat, is going to be our specific heat, which is 2.5 joules per gram degree Celsius. We're going to multiply that by the mass, which was 10 grams in our problem. And then we need our change in temperature. Now we went from negative 150 to negative 97.6, so our final is negative 97.6. We write that first, minus the negative 150 degrees Celsius. Okay. And I calculated that out already, and I ended up getting 1,310 joules. And that is also going to be equal to 1.3 0.31 kilojoules. Okay, I'm going to go ahead and do that conversion. So I just divided by 1,000 to get that. All right, the next part, we want to do the melting. So let's do that melting. We know that we have 10 grams. We know from up above we already did the molar mass, and this was 32 grams per 1 mole. And we know to melt it was 3.22 kilojoules per mole. Okay. I get 1.01 kilojoules. So that's why I converted this one to kilojoules. In order to do that, we just divide by 1,000 to get the kilojoules. Or we can do another conversion if we want. Okay, so that's the process of melting. Now we're going to go back and we are going to do the heating of the liquid. And heating the liquid is going to go from negative 97.6 to our boiling point temperature, which is 64.7. All right, another Q equals Cm delta T, so Q is going to be 2.5 joules per gram degree Celsius. That sometimes actually changes depending upon temperature. I'm just going to use that as a constant for now to simplify our problem solving. Okay. 64.7 is our final temperature minus the negative 97.6. Okay, I get 4060 joules, which is going to be 4.06 kilojoules. So I'll go ahead and put those together. So first three. Okay, let's keep going. Now we're going to do the next process, which is vaporizing. So we're going to vaporize or evaporate. $10 grams, 32 grams per mole. For every 1 mole, it was 35.2 kilojoules. Do a calculation on that, and I got 11 kilojoules. And then the last part of this is going to be heating the gas, because we did go all the way up until we got to 103.5. So let's heat the gas from the 64.7 to 103.5 degrees Celsius. So last step, and then we're going to have to add all of these together. I guess I can underline that one so I make sure I keep track of which ones I need. Okay, so Q equals specific heat times 10 grams times 103.5 minus 64.7 degrees Celsius, and I get 970 joules, or 0.970 kilojoules. Okay, so what we want to do at the end is we want to actually add all of these values up. Okay, so total energy to heat from negative 150 to 103.5 degrees Celsius, and we go ahead and add these all up. So 1.31 plus 1.01 plus 4.06, 11, and 0.97. Okay. And those are all in kilojoules. And so when we do that, I got 18.35 kilojoules. And this should be the total amount of energy. So we can work that any direction that we would like to. I hope that was helpful.